Welcome back to our next section. Right, next section is about the section 3.3. Right, the third section in chapter 3, which we have seen that there are totally 7 or 8 sections in chapter 3. That's the third one, right? And last time we have seen the basic properties, but as we have mentioned, everything is very, very simple functions, such as the basic ones, or the parent function in other words, and the linear combinations, which yields to some polynomials or some simple trig functions and exponential functions. If you remember, we had different rules as written last time. And this chapter here, or this section, is not only the scalar product, but the function product. Right, this section is about product rule, quotient rule, and higher order derivatives. Well, the product rule, quotient rule means, well, we will not only see a simple function enough, but we will see a product of functions. For example, the product rule is taking the derivative of u times v, where u is a function of x, v is a function of x. Where u is the f of x, v is g of x, well, there are two different functions that we take the derivative to be u prime times v plus v prime times u. Right, so that's a product of two functions. First of all, identify them, then take the derivative of first one times the second plus derivative of the second one times the first. That's our property and how to use the product rule. Right, so that's our product rule. Alright, a little clear. Well, I hope it's able to distinguish. I keep them written so different, right? The product of the first derivative times the second plus the product of the second derivative, or be clear, the derivative of second times the first. Right, so that is the product rule, which kind of is extra term. Right? We have the one term expression into two term expressions. So to prove it, of course, where u is f of x and the v is g of x as the view of functions, right? There are two different functions, and the product simply means they are the product of two functions together. And to prove it, right, in the view of function, they are fx times g of x, and we use limit definition as h goes to 0. We have that expression, right? The difference of y, which is substituting x plus h to the function, and minus the original f times g, right? F times g of x plus h is f of x plus h times g of x plus h. That's what the basic property from our pre-calculus had seen before, right? From previous semester. Then in order to make it a quotient, or to make it a simplifiable items, what we can do is to add something and subtract something to make them separated into two expressions, right? That's our purpose. So what we do is, well, since we know that it may be true that, well, the formula to be proved that they are the derivatives, right? So what we do is we're seeking for the term to make sure, or to fix it, to make it has the derivative with it. Right? Such term like we have the first two is subtract the common factor of g of x plus h to get the derivative of f. And over here we get the common factor of f of x to get the remaining, to see what we have, right? Of course, that middle term is, we subtract and add, it will yield to 0, but in that way we are able to separate the functions. Like the way we called before is called factor by grouping. Right? So that was the middle one. We attached this term and this term. Right, that's the middle term we attach. Therefore, by definition, right, or by something, we're able to factor out the g of x plus h. And for the division of h, of course, it could be separated, right? The second term also could be able to factor out f of x. What we have seen is the expression of 2. Right, then afterwards, we are able to separate into two limits, since that's two expressions. If the limit exists, then both of them could be separated. That are separated into two expressions, and the product, the limit of the product also yields to the product of limits. We could this one, well, the f of x is the function of x treated as coefficient, just carry it out. And the limit of h goes to 0 when g of x. Right, that one we separated and we get, well, this part f of x plus h minus f of x over h is the definition of f prime. And what we get, the limit h approach to 0 of g of x plus h is same as g of x. And this one, if we revise the order, right, that will be f of x times g prime of x, or g prime of x times f of x. Right, that we get here from the product of f times g, we'll get f prime g plus g prime times f. Where if we go back to uv, that will get u prime v plus v prime u. Right, so that is the proof of product rule. Use the limit definition. Right, the purpose is to get a common factor and separate into two things. To get that into the form of difference of quotient, then we are able to get the derivatives at the end. Of course, the largest condition is, well, f and g, their derivative exists, right? Then we can do the limit definition. They have the derivative. So on their domain of the differentiation, right? On their domain of derivatives. Right, so anyhow, that is the product rule. So when we do a question, right, so for example, let's see if the product rule is working. I find the derivative of fx equals 3x squared minus 1 times x plus 2. Well, first we can see when we simplify, f of x. Here simplify means expand. Right, so it's in other words, it's expand f of x first. Well, second one is apply product rule. Well, once we expand f of x, that's what we will get is a simple polynomial, and everything else will be doable, right? So let's try. F of x equals 3x squared minus 1 times x plus 2. This one we can simply FOIL it, right? 3x squared times x, that's 3x to the third. 3x squared plus times 2, that's 6x squared. Negative 1 times x, negative 1 times 2. Right, that's what we get for f of x. Then we do f prime of x. That will get, well, 3 times 3x to the second plus 6 times 2x minus 1 minus 0. Right, apply the power rule here, right? The power will carry down and the exponent minus 1, right? If you get it fast enough, you can try to do that, or later to be faster, that may be a little easier, right? A little more faster. A little more faster. 9x squared with product is plus 12x minus 1. That is the f prime of x we get. Well, when we apply the power rule, we expect to get at least same format, right? So apply the power rule here. So first of all, we have the product of two expressions. First expression is 3x squared minus 1 multiplied by the second expression to be x plus 2. Right, so we're able to identify them first. Identify the u, identify the v. That's what the formula tells us to do, right? U and v. And what we do is u prime times v plus v prime times u. Right? Be careful to keep the order because later we have quotient rule that order is really matters, right? Since we will see later. Right? The quotient rule is a little different, but similar. Then u prime is what we need the derivative of that. That's 3 times 2x minus 0, that's 6x. V prime will be derivative of x is 1 plus 0, that is 1. Right? That we get the formula, so f prime of x will be u prime times v plus v prime times u. Right, just apply the formula that u prime times the v, v prime times the u. And first and second, right? First path and second path. U prime 6x times x plus 2, keeping parentheses will be a better way. Sometimes keep both of the expression inside the parentheses, may a little help. V prime times u, u prime times v. Right, then after that we are expect to expand it, that we get 6x squared plus 12x positive 1 times 3x squared, positive 1 times 1 times negative 1. What we'll get is common what is it? Simply like terms, right? Combine the like terms. What is it called? 9x squared plus 12x minus 1. Well, which we see well in the example, right? Either we simplify or expand it first, it will give us derivative in this format. And if we apply the product rule, it looks like, well, a little more steps, but actually it's easier in calculation. Right? So maybe the risk to expand it is it is more risky than afterwards we multiply, right? Since the power after we apply the power product rule is a little lower. Before that it was a little higher. It has risk to multiply it wrong, right? Higher risk. But over there, maybe it's a little easier. Right? Just we combine the like term and we'll get the same result. So try to use product rule if we could, right? Try to get familiar with it. And for some other expressions, simply product rule will not help us. I mean, simply expand the function will not help us. Right? We'll see. We have to use product rule as the aid to help us to find the answer. Right, so try. Find the derivative of y equal x e to the x, which that's a product of x times e to the x. Right, so still we have to use the product rule to identify them. Why? We have the product of x and e to the x. Therefore the u prime is the derivative of x, v prime is the derivative of e to the x, which is e to the x as well. Right? The derivative of x is 1, derivative of e to the x is e to the x. Then we apply the rule, u prime times v plus v prime times u. Cross it. U prime times v plus v prime times u. Right. that we get 1 times e to the x is e to the x, and e to the x times x is x e to the x. If you want, you could factor it to get e to the x times 1 plus x. To leave in this format is fine. To factor it out is also okay. Right? Either one is accepted, since both of them has clean enough expression. Right? We don't have clean enough means we don't have the expression with negative exponent also. Right? That's what is good enough. Let's see the next example. You can try also, right? Find the derivative of oh, we have a linear combination. Right? We have 2x cosine x minus 2 sine x. Right, the first expression is a product that 2x times the cosine x. The second one is not product of function. Right? It's just scalar multiply. We have a negative 2 multiplied by a sine of x. So we need to apply the product rule only for the first expression. The second, if you apply it, that same thing, right? If you apply 2 times sine of x, that will be same thing, but by looking at it, right, we already know that's negative 2 times cosine x will be its derivative, right? So for scalar multiply, we never have property say to multiply, use product rule, right? Product rule only need to be applied when it's function times function. Right? So for the expression of 2x cosine x, u is 2x, v is cosine of x, right, the first and second. So u prime will be 2 times 1 is 2. V prime is negative sine of x. I hope you will still remember the property, right, or at least try to memorize it, or at least have it on the side of your material. You should have it somewhere. That's what we have. Right, so f prime of x could be done that, well, the first underlined part should be the following the derivative of product rule, u prime times v plus v prime, that's negative sine of x, times u. Right, that's the first one underlined expression to be get that, right? U prime times v prime times plus v times v prime times u. Then the second part we have negative 2 times the derivative of sine x is cosine of x. Right, simplify a little bit. We have 2 cosine x. We have negative sine x times 2x, that's negative 2x sine x. And the third expression is minus 2 cosine x. And after we simplify, right, usually we stop there, but after that we see, well, 2 cosine x, negative 2 cosine x are exactly opposite to each other, but they can be cancelled. What we get is negative 2x sine of x. The single expression we left over at the end is negative 2x sine of x. Right, that is the product rule. And you will see more examples or more practice in homework for that. And similarly, as another thing we have mentioned was the quotient rule. That we get is a quotient, u over v. We want to find the derivative of u over v, that is u prime times v, v prime times u on the numerator, but in the middle connection is a negative sign, u prime v minus v prime u over the square of v, over v squared. But still that they are functions. Right, the quotient of functions will yield to a quotient rule, that is the top derivative times bottom minus bottom derivative times top over, originally was the bottom denominator, then it becomes the square of the denominator. Try to prove. I try to prove it, use the limit definition we got before. Of course, everything satisfies its condition. That means in the case of g is not equal to x, everything is differentiable on its domain. Then the quotient will be the intersection of each domain. Right? That we get this quotient rule. Right? It means every function is differentiable in each domain. Then u over v is only exists when the intersection of the derivatives domain, domains of each derivative. So try to prove it, use the limit definition, just don't think too much about the domain, just like what we had shown before was the proof of product rule. Here quotient is very similar. So let's see. Let's see an example. Find the derivative of y equal f(5x minus 2) over x squared plus 1. That is a rational expression. Right. So for rational expression, which is not similar as what we've seen before, what we see was something like y equal 2 over x to the second in the term that we're able to flip it up to get the derivative, right? That we get is coefficient still, right? That is still a coefficient of the expression. That is 2x negative 2. Oh, we still have a scalar in front of our function. Here is function over function, which we need to apply is the quotient rule, right? The numerator is a function of x, denominator also contains the x. Right, so we need to identify like the product rule. The step is first of all identify them. We let u to be the numerator, we let v to be the denominator. Right, then the u prime, if I still show you the whole process. Right, 5 times the derivative of x is 1, minus derivative of 2 is 0. And the v prime is derivative of x squared is 2x, of 1 is 0. Like that we get the u prime and the v prime. Right, so the quotient has derivative of the denominator is square of v. We could write it first if you want, since that is a simpler expression. We could write it first if Like personally, I like to write it first because it is a simpler expression. Right, numerator is a little more things to do, right? U prime times v minus v prime times u. U prime is 5, v is x squared plus 1, minus v prime is 2x, and the u is 5x minus 2. That we get u prime times v minus v prime times u, right, that expression. Then apparently we need to simplify it, right? That we get the square of x squared plus 1, we get numerator to be 5x squared plus 5, and we get negative 2x times 5x, that's negative 10x squared, negative 2x times negative 2, that's plus 4x. Right, that we get in the descending order, which means to get power from higher to lower, I get 5 minus 10, that's negative 5x squared, plus 4x, plus 5. Right, you don't have to do anything with it. If you want, you could factor the negative sign, each negative sign out, right, but it's not necessary. They to be formed like that, to keep the last final form like that is totally acceptable. If you want, you could factor the negative sign out to get 5x squared negative 4x minus 5 over x squared plus 1 squared. If you want, you could do that, but not necessary again, right? I mean, it's not that necessary to do so. Right, but still, either the product rule or the quotient rule, we need to do is identify the u and the v, right? To be using the quotient rule, the u and v are more strict, that we have to make the numerator to be u, we have to make the denominator to be v, to make sure is what we use the correct formula, right? If we go opposite, then it will affect the formula, which means it will be wrong, right? So we have to let the numerator to be u, the denominator to be v, right, to get the correct answer. Which it is still straightforward, right? Just apply the formula and you will see what to do, right? Or after you get it. Let's see more exercise. I try to find the derivative of f of x equal x over x plus 5. That, well, we can try it for your own, then continue to see what the result is. I give you seconds to do so. Times up, then we see what we have. U equals x, v equals x plus 5, the numerator, the denominator, v to be distinguished, able to be distinguished. Then the u prime, of course, is 1, then v prime is also a 1, right? Could go a little faster, then you're still able to follow, right? 1 plus 0 basically is still 1. Right, then f prime of x, apply the quotient rule, that is the u prime v minus v prime u over v squared. So get u prime times v minus v prime times u over v squared. That the v squared still need to be kept down on the denominator, and then u prime times v, that is 1 times x plus 5, and negative 1 times x will be v prime times u, that is minus x. That we'll get is 5. Over x plus 5 squared. Right, that's what we get for the quotient. But still, when we apply it, right, the first we do is product of u prime and v. Second is the product of v prime and the u. The connection is different signs, so be super careful that do not mix it around. I do not switch the order. When we find the derivative of y equals sine x over e to the x, that we can still apply the quotient rule, right? Since here is the quotient of sine x over e to the x. When we have a quotient of functions, then we get the quotient rule, right? That we have identified the u and the v first. U is sine of x, v is e to the x, where the u prime is cosine of x and derivative of v is e to the x, right? That's what we need for the quotient rule. Then we are now getting it, well, it should be u prime times v, v prime times u, first and the second path we have. Therefore the y prime is u prime times v cosine x times e to the x. When it's all single expressions, you could put parentheses, we don't have to put in parentheses. Right, minus v prime, recommended of course to put everything in parentheses, times u. Of course, recommended is to put in parentheses to make sure that we are doing the right thing, then then afterwards we getting more familiar to the formula, then we could omit the parentheses, if available, right? Then the bottom is the e to the x squared. Well, in other words, that's e to the 2x, but e to the x squared is a little easier to see since we figure out, well, the numerator has both e to the x. We could do something with it. Right? Be careful with division. Is that for the division we cannot divide the single term. You could, but you need to do simultaneously together, right, everything. So it will be a little more benefit when we do factor out. We have both e to the x in the expression, that we factor it out to get cosine x minus sine x over e to the x squared. Now it's clear to see that e to the x will be cancelled out once. E to the x squared will become e to the x, by 1 power less. That we get e to the x on the denominator still. The numerator is cosine of x minus sine of x. the next thing is the formula of the remaining trig functions. The derivative of tangent is the secant square of x, which means, in other words, that the square of secant x. For trig functions, we could put the power in the middle, right? But definitely that means it's the square of the trig function, square of the trig function. And b dx of cotangent x is negative cosecant squared. And the derivative of secant of x is secant tangent. And derivative of cosecant x is the similar format as secant tangent, which is called cosecant cotangent but has negative sign. Negative cosecant cotangent. And somehow we can feel that it has pattern within, right? So that thing, if we read more, that will be not so hard to memorize, right? So we have the other four trig functions has the derivative in that. Alright, so we take the derivative of tangent to prove. Right? Or not exactly prove, but illustrate. The tangent is sine over cosine. The derivative of that, right? Therefore, we can get u to be sine of x, v is cosine of x, that we get u prime is cosine, and v prime is negative sine. But that's no problem. Therefore, the derivative of tangent x is u prime times v minus v prime times u over the square of v, right, cosine squared. That we will get is cosine squared of x, negative minus sine of x times sine of x, that's plus sine squared of x. Cosine squared plus sine squared of the same angle is 1, 1 over cosine squared of x. Where we have the Pythagorean relationship here, right? Originally we use quotient, here is the reciprocal relationship, that 1 over cosine is secant. Right, so that is how we get the formula of tangent, use quotient rule. So try the cotangent. Right, similarly, it should be done. Cotangent is cosine over sine, so similar way.